Recent attention in instance segmentation has focused on query-based models. Despite being non-maximum suppression-free and end-to-end, the superiority of these models on high-accuracy real-time benchmarks has not been well demonstrated. In this paper, we show the strong potential of query-based models on efficient instance segmentation algorithm designs. We present FastInst, a simple, effective query-based framework for real-time instance segmentation. FastInst can execute at a real-time speed while yielding an AP of more than 40 on COCO testset. The key designs of FastInst include instance activation guided queries, dual path update strategy, and ground truth mask guided learning. The experiments verify the effectiveness of FastInst. Now, we detail our method. The whole contents include 3 parts: background, the method we propose, and the experiments. Instance segmentation aims to segment all objects of interest in an image. The mainstream methods like mask RCNN follow the design of detection then segmentation. Despite being simple and intuitive, those methods generate a lot of duplicate region proposals that introduce redundant computations. To improve efficiency, many single-stage methods built upon fully convolutional networks appear. The inference speed of such methods is appealing. However, due to the dense predictions, the classical single-stage methods still rely on manually designed post-processing steps like non-maximum suppression. Recently, query-based single-stage instance segmentation methods have emerged. They exploit the versatile and powerful attention mechanism combined with a sequence of learnable queries to infer the object class and segmentation mask. However, the superiority of these methods on fast, efficient instance segmentation has not been well demonstrated, which yet is critical for many real-world applications such as self-driving cars and robotics. The efficient real-time instance segmentation benchmarks are still dominated by classical fully convolutional models. In this paper, we propose a very simple and effective method named FastInst. This method closes the gap between the real-time fully convolutional methods and query-based methods, showing the great potential of query-based method in efficient instance segmentation algorithm design. This figure shows the speed-performance trade-off on COCO testset. All models employ ResNet 50 as the backbone except Orion mask with DarkNet 53. Our FastInst surpasses most state-of-the-art real-time instance segmentation algorithms in both speed and accuracy. The key techniques of FAST include 3: instance activate guided queries, dual path transformer decoder, and ground truth mask guided learning. Initial queries play a crucial role in query-based architecture. One of the reasons for the slow convergence of DETR is that its object queries are zero initialized. Although learnable queries mitigate this issue, they are still image independent and require many transformer decoder layers to refine. To resolve this problem, we propose instance activation guided queries that straightforwardly pick the queries with high semantics from underlying multi-scale feature maps. These high semantic queries contain rich embedding information about potential objects and reduce the iteration update burden of the transformer decoder. Specifically, we first predict the class probabilities for each pixel, and then dynamically pick the pixel embeddings with high class probabilities as the initial queries. To avoid redundant query selection, we follow a local maximum first selection strategy that first pick the queries with probabilities that are local maximum in the corresponding class plane. During training, to activate these query embeddings, we employ Hungarian matching with an instance location cost to assign the supervision target. Note, deformable DETR also selects the queries from the underlying features, but they require prior anchor boxes to guide the query selection while ours do not. The second technique is dual path transformer decoder. This technique co-optimizes the pixel and query features in the transformer decoder, aiming to reduce the dependence on heavy pixel decoders and meanwhile acquiring more fine-grained feature embeddings. The whole process is like an expectation maximization clustering algorithm. E-step: update pixel features according to the centers, that is, queries. M-step: update the cluster centers. The third technique is ground truth mask-guided learning. We employ masked attention in transformer decoder for better segmentation performance as described in mask-2 former. However, masked attention restricts the receptive field of each query and may cause the transformer decoder to fall into a suboptimal query update process. To mitigate this issue, we use GT mask instead of predicted masks to forward transformer decoder again. The new output is supervised according to a fixed matching, consistent with the last layer's bipartite matching results. By such guided learning, we allow each query to see the whole region of its target predicted object during training, which helps the masked attention attend within a more appropriate foreground region. The last part is our experiments. We first show the ablation studies that verify each component of our proposed method. As shown in tables, FastInst benefits from all three proposed techniques. The instance activation guided queries perform better than other methods, especially when the transformer decoder layer number is small. Dual path update strategy consistently outperforms single path update strategies. And the ground truth mask guided learning improves the performance across different backbones. This table shows the comparison of FastInst with SOTA methods. FastInst outperforms most previous real-time instance segmentation algorithms in both accuracy and speed. Here the FPS is measured on a V100 GPU with a batch size of 1. Notable, FastInst is the only algorithm in table with AP greater than 40 while maintaining a real-time speed. One advantage of query-based architectures is that it can unify the image segmentation tasks. According to the practice of mask-2 former, FastInst can easily transfer to other segmentation tasks like semantic segmentation and panoptic segmentation, and show the superiority. These figures visualize some predictions of FastInst, including two typical failure cases. That is, the duplicate predictions and the over-segmentation. In sum, we present FastInst, a simple query-based model for real-time instance segmentation. FastInst achieves excellent performance on instance segmentation task while maintaining a fast inference speed. We hope this work can serve as a new baseline for real-time instance segmentation and promote the development of query-based image segmentation algorithms. All code and pre-trained models have been released on GitHub and ModelScope, the largest model community in Chinese.